Question 5, page 123. A fair spinner with 5 equal divisions, A, B, C, D and E, is spun 100 times. So I've got A, B, C, D, E on a little spinner, so it's a 5-sided spinner. How many times would you expect to land on an A? Well, if this is a fair spinner, then a fifth of the results will be A. And a fifth of 100 spins is going to be 20 A's. Next one, how many D's would you expect? Same again. A fifth of 100, because a D represents a fifth of what's on the surface of the spinner. 20 D's. Julie spins the spinner. It's the same spinner. She spins it only 10 times, and she gets 2 A's, 3 B's, no C's, 5 D's. Doesn't even mention the E's. She then says, that this shows the spinner is biased. Is she correct? Well, from the question we know the spinner is totally fair. It says so. But let's look at what she got. So for A she got 2. For B she got 3. For C she got nothing. For D she got 5. And for E she got nothing. It doesn't say so in the question, but she can't have got any E's. None were listed there. Now remember, you'd expect 2 from each since it's a fair spinner. And she says she reckons it's biased. Is she correct? Well, she can't be correct. For a start, we know it's a fair spinner. But look at that. Half the ones that turned up as a result were D's. You're going to have to say no, because too few trials. So each spin is considered a trial. You're trying it, you're recording it, you're trying it, you're recording it. So no, too few trials were carried out. So you cannot tell. And that's the thing about relative frequency. If you don't do sufficient trials, the results you get will not be reliable. Okay? It is quite is a really good question. Over a long period of time, it is found that the probability of a faulty bulb is 0.01. I think I'll put it up here. So probability of a faulty bulb is 0.01. Alright? How many light bulbs would you expect to be faulty in a batch of 500? Well, each one is 0.01 probability of being faulty, and I've got 500 in my batch. So 0.01 times 500, I can do that. Chop off those 2 zeros, I'll get 5 faulty bulbs. One day a light bulb checker finds 17 faulty bulbs. Estimate how many bulbs she had checked that day. Well, it's the same probability, the same relative frequency, so we're going to say 17 out of a certain total must come to 0.01. We've set up a little equation here. So 17 over the total that she checked comes to 0.01. So rearranging, we have 17 equals 0.01 times mystery value x, the number she checked. So x is going to be 17 over 0.01. Grab your calculator, you should get 1,700 bulbs that have been checked. Alright, dead easy. That's too long. Going over to the other page now, we should have a graph ready made. Question H, yes, there it is. Right, this is Carly. She has a splitty that her spinner lands on a pink, so she's conducting an experiment basically. She spins it 100 times and calculates the relative frequency of getting a pink after every 10 spins. These are her results. Now, thanks to Carly, she's already calculated the relative frequencies for us. Use the graph to work out the number of times the spinner landed on a pink after 10 goes. Now, let's take a look. After 10 goes, that's that there, the relative frequency was 0.6. So after 10 goes, we've got 0.6 multiplied by 10. That gives us 6 pinks. Is that alright? That's how it's worked out. It's dead easy, isn't it? So what Carly actually recorded was 6 pinks out of 10, hence the first relative frequency of 0.6. After 50 spins, there's 50 right there. So we grab that result. That looks like 0.44 to me. So there's the relative frequency of 0.44 that Kylie worked out. She did 50 spins, multiplied by 50. I think that answers 22 pinks. Let's just check that to be absolutely sure. So 0.44 times 50. Yep, exactly 22 pinks. B, from the graph, estimate the probability of the spinner landing on a pink. Now, the more trials, the better. The more trials, the more reliable. So I'm going to go with 100 spins, maximum amount that Kylie did, and take that relative frequency right there. So the best thing to do is to calculate the probability just by looking at that relative frequency, because we're going to trust that with 100 trials it's going to be very, very close to the expected value. So that's exactly on 0.4. Therefore, probability of landing on a pink using relative frequency directly is 0.4. And it's an estimate, it's an experiment in 9 on page 124. Bit of a tricky question in places, this one. Right, Izzy's rolling a fair dice after every 10 throws. She works out the relative frequency of getting a score of 1. Now, if it's a fair dice, perhaps they would expect every number to score 1 over 6. So each dice, each face will have an equal chance of coming up. So anyway, let's look at her experiment there. She's calculated the relative frequencies for us. After 20 throws, how many ones did she get? So 20 throws relates to that relative frequency right there. So we can have 0.25 multiplied by 20 rolls of the dice. A quarter of 20 is 5, so we've got 5 ones. How many ones were thrown between the 21st throw and the 50th throw? Well, here's the 50th throw. Relative frequency is 0.1, so it's 0.1 multiplied by 50. The answer is also 5. So the strange thing is, even though she's thrown an extra 20 throws of the dice, she didn't get any more 5s. Therefore, how many ones were thrown between the 21st and 50th throws? No more ones were thrown. Is that clear? Now, do you think the dice is biased? Well, let's have a look. I know that the probability, working down here, the probability of getting a 1 is going to be 1 out of 6, and that's going to give us 0.16 recurring. I just remember that one, and that's approximately 0.17. Now, if I take these 100 throws just there, and trusting that the more throws or more trials or more rolls in this case that I have, the more reliable will the relative frequency be, and hence the theoretical probability. I think I'm sitting on 0.11, so I write down 0.11 here, and I can see actually by experiment that's actually very close indeed. So therefore the dice is completely fair. The relative frequency calculated after 100 throws matches the theoretical probability of 1 over 6, which is 0.16 recurring. Therefore it's totally fair. Next question. Right, what have we got here? The table shows the frequency distribution after throwing the dice 270 times. This is question 10. So a 1 came up 52 times, a 2 came up 56 times, a 3 came up 41 times, etc. So I'm going to try and squeeze some answers. Actually, let's do it down here, it'd be better. So A then, it asks us, what is the relative frequency of getting a 2? Well, so the relative frequency of getting a 2, again, you don't have to do this like this in the exam, it's just me teaching, would be 56 2s out of the 270 rolls of the dice. So I'm not going to simplify that down, I'll leave it as it is. B, what's the RF of getting a score greater than 4? Well, greater than 4 is that one and that one, which is 79 plus 4 plus 5, 84. So that's going to give me 84 out of 270, and that's the relative frequency of getting something greater than 4. Not 74, greater than 4. C, what's the relative frequency of getting an even number? Well, let's just rub out the 5, it's not an even number. So I want 56 plus 37 plus 39. I'll quickly add it up. 56, 37 plus 39. That gives us 132 out of 270. That would be RF of an even number. Now, I said I don't have to simplify these. No reason why I should leave it as a fraction, but I can convert them all into decimals. It's quite legitimate to do that. Which is dead easy with the calculator. Just go 56 divided by 270, etc. Right, D. What's Ellie's problem? Ellie says the relative frequency of getting a score of less than 3 is 149 over 127. Less than 3, she says. Well, let's have a look at that, shall we? Less than 3. Well, that'll be that one and that one. What did she do? Oh, I think she added on the 3's as well. 52, 56, 41 comes to 149. So no, she shouldn't have added that 51. The question says, is she correct? So Ellie is wrong, and I'll tell her when I see her. It should be. So let's give the right answer. Yet no marks for saying she's wrong. Ellie is wrong. It should be 108 out of 270. So she included the results for getting a 3. The exclamation mark won't hurt. One of the frequencies is the same as the result you would expect from theoretical probability. So which one is it? Well, I've got 6. Do it up here, away from the little image down there. So for E then, I've got 270 rolls of that dice. I'm going to divide that by 6 possible outcomes, and I will get the exact number I would expect. So 270 divided by 6 possible outcomes gives me 45. Now look at that. According to this, the 5 came up exactly 45 times, so that's the one that we're going to have. All right. Therefore, which one of these frequencies is the same? Therefore, the frequency for 5 came up exactly as predicted. Let's just rub that out. That should say according. According to theoretical probability. I could, of course, have said 1/6 of 270 and worked it out theoretically that way. I've got exactly 45. It's the same thing. Alright, next question. Fair spinner. Here we go. This is really nice. A fair spinner is made from a regular octagon. So I reckon I've got 8 sides there. Put a little 8 there. Each of the there it says. Each of the 8 sections of the spinner has a letter on it. P, Q, R, and S. Let's just move that naughty little clock. There you go. You can see it now. P, Q, R, and S. It is spun 240 times, and there's the results in the table. How many times does each letter appear on the spinner? Sounds terrifying, doesn't it? Well, if I've got 8 possible outcomes, I'm going to take my 240, divide that by 8, and I will get exactly 30. So if a spinner occurs just once on my 8-sided spinner, I'd expect it to come up about 30 times. Well, look, the P, that's about 1 times 30, isn't it? The Q, that's roughly 2 lots of 30. The R is almost 90, that's roughly 3 lots of 30. And the S, well, that's nearer to 60 than 30, and it's definitely a fair spinner, so I'm going to call that 2 lots of 30 approximately. So therefore I've got 1 P, I've got 2 Q's on there, I've got 3 R's, and I've got a single S.